Okay, so officially welcome to class number 2 of stellar spectroscopy. And today I'm going to actually bring up the notes. Okay, and I'm hoping this will be a little bit more helpful. Now, if you haven't done so, I'm going to highly recommend that you read Mike Briley's statement. Okay, I have my own strategies. I print it out. I leave it somewhere in the house where I usually do my daily constitutional. 2 or 3 times into it, I've read it. So, you know, whatever works for you, not to be distasteful. But anyway, it talks about those microturbulence. It talks about excitation states. And it talks about the temperature. Okay, and it talks about the density and pressure and the gravity of the star and how all these things affect the spectrum. And it's actually quite good. So I feel like I've kind of given you the highlights where it goes. We talked about what all the fuss was about, the absorption line, and then we reviewed what the equation is for an absorption line. This is from radiative transfer. We'll go through that later, how this equation comes to being. This is the measured light. This is the continuum. This is the radiative transfer term. This is the optical depth, which we defined as the integral along the line of sight through the gas cloud of the opacity, which is a function of wavelength. So there's a value at each wavelength. It's not one thing, it's another. Okay, how's the video coming through? Can you see things okay?
It's fine.
Okay, thank you. Okay, so that was the opacity, and that the opacity was the density times the cross-section, where this is the number density of the absorbing particles. And remember, each absorption line comes from one single type of particle, like singly ionized magnesium-2 in the first excited state gives rise to an absorption line in the spectrum. So that would be the density of that particular ion in that particular excitation state. The absorption cross-section, okay, is a very complicated beast, okay, and it is defined, this is review, as the power removed from the beam divided by the flux in the beam. Has units of centimeters squared, so sometimes you can sort of think of it as an actual physical cross-section. Like the cross-section of the Bohr atom for Lyman alpha absorption is very close to the Bohr radius, which is the physical size of the radius of the inner electron. But it actually is a quantity which describes how much power, the rate at which energy is removed from the beam divided by the flux in the beam. It's a unit, sort of, you see what I'm saying? You have a certain amount of flux coming in, and then the atoms remove, a single atom will remove a certain power, certain energy per second. Okay. We talked about that it depends upon the atomic physics. We'll talk about the natural broadening profile coming forward. It also depends upon, from the Doppler shifts, the line of sight velocity distribution of the atoms, okay, because atoms moving toward you or away from you, they're moving toward you, they will absorb light that's a little bit bluer than the atom at rest, and atoms moving away from you will absorb redder, okay. So you have the thermal motions, you might have turbulent motions, you might have collisional broadening, you might have rotational broadening, we talked about that. So the final cross-section can be the convolution of all these terms, okay? The final cross-section, you've got the natural, which is the atomic cross-section based upon atomic physics. Only depends upon what's going on in the physics of the atom. The thermal, which depends upon the temperature of the gas. The turbulent, which depends upon the bulk motions in the gas. The collisional, which is basically the pressure broadening term. And then if you have a rotation of the star. So these, in a sense, this is really the only true cross-section. We'll talk about it later. As I rewrite these notes, these are actually velocity redistribution functions, or basically absorption wavelength redistribution functions, but you convolve with the natural cross-section. But in the end, this is all couched together in something called the total cross-section. Okay. And then, we talked about, to get the number density, you need to know the geometry of the gas, the hydrodynamic state, the chemical abundance, the ionization balance, the radiation field in and around the gas, and the temperature of the gas. And to get alpha, you need to know the temperature of the gas, the atomic physics of the absorber transition, dynamical motion of the gas, rotation rate of the star. See, all this physics is hiding in the shape of that absorption line. Okay. So you need to do sophisticated modeling. Then we talked about that the optical depth is the opacity over the path length. The opacity was the number density times the cross-section. If you pull the cross-section out thinking that it doesn't change along the path length, you get it outside the integral. You have an integral of the density times the path length, which we redefine as the column density. And we obtain tau equals the column density times the cross-section, and can rewrite the absorption line profile as the counts at a given wavelength are the continuum counts times the radiative transfer, which is minus tau, which is now column density times cross-section. How many people have seen this before last week? One. Good. So some of this is review. I hope it was a good review, helpful review. Okay. Now, let's talk about these graphs. Hopefully one of your accomplishments today will be you will walk away from class being able to look at an absorption profile and pick anywhere along the absorption profile and basically take a guesstimate of what the optical depth is at that point in the profile. All right. In practice, one has a lot of free parameters in the physics. Okay. That is, again, the temperature, the rotation, the turbulence velocity, etc. To get all of this cross-section information, then using n times alpha, okay, if you know all the physics that goes into it, you get this as a function of wavelength, then you can use the absorption profile to hopefully fit the data to calculate the column density, okay, and do a chi-square fit to your profile of some sort, and get this out. You model this. This takes a physical model. You then fit your physical model and get out a column density. So your column density depends on your physical model, and you're measuring it based upon the shape of a line. Okay. So what we're going to do is I'm going to show you some optical depth profiles, and I'm going to show you some normalized spectra profiles. And I'm going to make an assumption that the cross-section of these is the natural cross-section convolved with a thermal broadening. Okay? Maybe you've heard of a Voigt profile. When you convolve natural with a thermal, you get something called a Voigt profile. I'm going to assume that the velocity distribution, the sigma of the line of sight velocity distribution, is 10 kilometers per second. Okay? And I'm going to assume a temperature of about 5,000 degrees, which is what gives you that sigma. Okay? It says with that or basically. So I'm assuming a gas of 5,000 degrees for these profiles, which results in a velocity dispersion of 10 kilometers per second in the gas. All right. So once I calculate the alpha from the gas, and I choose a column density to calculate tau, and I make this calculation, and I generate a profile. So here is, I'll choose, here's again my sigma v is 10 kilometers per second for 5,000 degree gas. And then I'll say, hey, I'm going to choose a column density of 10 to the 12.8. Okay? Column density, that means the integral of the density times the path length is 10 to the 12.8 atoms per centimeter squared. Okay? When I do that, I get an optical depth, tau, that does this as a function of wavelength. Now my central wavelength is 1215.6701. This is the Lyman alpha transition of hydrogen. Hydrogen that's neutral in its ground state. Now, so the peak optical depth is around 0.5. This is 1, dashed line at 1. Okay? When I have this optical depth profile, again, from alpha lambda, and then multiplied by that column density to give me tau, this is what my profile looks like. So here is, again, the optical depth, tau, and it goes up to 0.5 in the core, and then here is my absorption line, which is basically taking this profile, taking the exponential of minus that number, and that gives me this ratio.
Wait, who's the dotted line?
This line. The dotted line is the tau. Sorry.
Just the optical depth?
Yeah. So this line here is this solid line here. Okay? Maybe that's a little funny, but that's the way I did it. Okay, so everybody see how now that when you have an optical depth of 0.5 in the core, you end up getting a line that comes down to about 0.6, or 60% of the, I should say maybe 40% of the flux is removed in the line core, because you're down to 0.6. Okay. Let's consider a higher column density. Let's go up to 10 to the 12.9 atoms per square centimeter. Okay. Same width, because that depends upon the dispersion of the gas, which depends upon the temperature of the gas. Now, with going up 0.1 in the log of column density, we now end up with a central optical depth of about 0.75. Okay, so here's my optical depth profile coming up to about 0.75. When I run that through this equation, I get the solid line, and now we're down to about 0.5 in the line core. So in the line core, when you got a 0.75 optical depth, you've moved about 50% of the flux. All right, let's continue on. Okay. Let's move it up to 13.1. Okay. Now at 13.1 column density, I get an optical depth of unity in the core. Okay. Notice the optical, that's a function of wavelength. So here's what it looks like, optical depth for a column density of 10 to the 13.1, okay, and a temperature of 5,000 degrees. It's 1 in the core. Here's the absorption profile that results from that. Bang. Now, this number is basically 1 e to the minus 1, 0.368. Okay? When tau equals 1, it's equal e to the minus 1.368. So there is your first bullet point for memorization of absorption profiles. When your optical depth is unity in the core, you will have a flux of 0.368 of the total flux at that point in the spectrum. Okay? That's what optical depth unity gives you. If you look at an absorption profile anywhere and the flux value, normalized flux is 0.368, you know that the optical depth is unity. I'll get to more of that in a second. Okay, let's move up to 10 to the 13.4 such that the optical depth in the core now is 2. We still have this broadening from the thermal properties of the gas, optical depth of 2. Okay? When we put that through our equation, e to the minus 2, or I'd say it's 2 actually at the center, the optical depth is changing. So optical depth 0, 0, 0, 0, optical depth rises, optical depth of unity, optical depth greater than unity. It's up to 2 up here in the core. This is 1. And here's optical depth of unity. Right. Yeah. So optical depth increasing along here. Gets to unity right there, and then goes up to 2 off the chart, comes down to unity. When you do that, what absorption profile do you get? Well, check it out. Now, with an optical depth of 2, you've got something down here, almost removing all the flux in the line core, almost 100% absorption, getting closer to it. But let's look where the optical depth is a function of wavelength. Where the optical depth is unity, which happens in two places in the profile on either side of the central wavelength. Watch. Optical depth unity. What's the flux in the line at that point? 0.368. Okay. Optical depth goes higher, profile's deeper, optical depth's coming back down. Unity, flux 0.368. Okay. So a lot of people, they think that optical depth unity, oh, that's when the line's gone to zero. Nope. It's when it goes wherever you are on the wing or in the core, wherever you are on the line, if the relative flux is 0.368, that's optical depth unity. So you can look at any absorption profile now and say, that's where the optical depth becomes 1. And in the core of the line, it's greater than 1, and in the wings of the line, relative to that point, it's less than 1, right? Relative to this point, the optical depth is greater than unity, and relative to this point, the optical depth is less than unity. Now you can read profiles, I hope, differently than you may have ever in the past if you've ever gotten into this business. Okay? And last but not least, let's crank the optical depth up pretty good. Here's 10 to the 13.7 atoms per cubic centimeter. Okay, now the optical depth goes up to about 4 in the core. Here's where it's 1. Okay, let's look at our profile. Boom, boom, boom. Hey, we effectively have removed all of the photons in the path at the core of the line. By the time your optical depth gets to 4, you've really, at that wavelength, those photons are basically almost virtually not getting through. Okay? You're counting almost 0 counts there. Again, as the optical depth increases along this optical depth function, when it hits unity, we're at 0.368. So it hit unity right here. Bam. So here's where we're greater than unity optical depth, and then these wings are where we're at less than unity optical depth, which are these regions here along the tau function. And last but not least, let's crank it up to 10 to the 14 atoms per cubic centimeter squared. Okay, optical depth of 10 in the core now. Here's unity. Okay, and now check this out. We really are not letting any photons through near the line core. Okay, near the 1215.6701 angstroms area, we are really not letting photons get through that gas. But photons that are near there are still pretty much making it through. And again, this is because of the velocity dispersion of the gas. There's fewer atoms at high velocity than there are at the central velocity. This, in effect, is almost the distribution of atoms along the line of sight. If this was 0 velocity with respect to you, these are atoms that are moving away from you, these are atoms that are moving toward you. And you can see that the number of high velocity atoms moving away from you is smaller than the number of low velocity atoms moving away from you, and vice versa. The most extremely fast moving toward you blue, the number of those is less than. It's just a Gaussian function basically along the line of sight. And so that's what causes these broad wings, is the fact that there's some atoms that are a small relative number of atoms that are moving at high velocities toward you, give you this blue wing, and then a relative small number of atoms that have the extreme moving away from you velocities. Most of the atoms are moving relatively slow with respect to you along the line of sight. So that's why the optical depth peaks there. And basically what happens, here's unity along the optical depth. That happens here. Okay. So here we're at high optical depth. There we're at low optical depth. That means basically that there's very few rapidly moving toward you atoms, and there's very few very rapidly moving away from you atoms that take out the flux out here at the velocity extremes of the absorption profile. So all that makes sense, I hope? Okay. So this is a really good one to study. I feel that it's a fairly instructive graph when explained along with it. Now, are there any questions at this stage? about the absorption profile and the optical depth and whatnot. Nope. Okay. So you're all pros. I could say, draw me an optical depth at the profile that has an optical depth of 2 in the core, and you could basically get it right. No sweat. Sounds like a good Kuhn question. All right. Okay. So now we've spent some time talking about the absorption lines, which are by far the easiest part of any spectrum to actually understand. One of the reasons is that the radiative transfer solution for pure absorption is extremely simple. Okay, when you get into the fact that the gas is also emitting light as a function of position along the line of sight, you have to include photons being added to the beam as well as being absorbed along the beam. So here you've got this beam. Photons here are getting absorbed from photons that were generated down here. Photons that are absorbed there, okay, that's great, but this area of the gas is also emitting light, some of it coming on, and it has an optical depth that changes. So, every point along the line of sight is absorbing and emitting, okay? And then this equation actually gets a lot more complicated, okay? So absorption is probably the easiest, pure absorption is probably the easiest to understand intellectually. But what I want to do is talk about things that are not absorption lines per se now, but what we call ionization edges, okay? Now, let's take hydrogen. Neutral hydrogen, for example, that's got the electron in the ground state. Okay? It takes a photon that has an energy equal to or greater than 13.6 electron volts to excite that electron so that it escapes the electromagnetic potential of the atom. Now, I said 13.6 electron volts or greater. Okay? I'm a photon. I have 13.5 electron volts. I come in, I see this neutral atom, I go, hey, boom, and the electron can go to some very, very high bound state, but I don't have enough energy to knock it out of the park. Okay? I come in, I got exactly 13.6 or something like that. I come in, I got enough energy, I just knock it right out of the park. It goes out into the gas with basically no residual energy. It's zero velocity relative to the center of mass of the photon in the atom that it got ionized. If I come in with, say, 14 electron volts, well, I've got enough energy. I come in and it's like, okay, I can knock that electron out of the park, unbound, and I give it some energy so it has kinetic energy in the gas. And that kinetic energy is measured relative to the center of mass of the photon and the atom. Photon's massless, but a little relativity and you can figure that stuff out. Okay, so that means that photons 13.6, 13.7, 13.710043, 13.8, 13.912, 20.7, 105.6, all those photons will have a propensity to be absorbed in the process of ionizing hydrogen. So now there's a whole region of the spectrum where you can get absorption. Everything above 13.6 eV, which corresponds to 912 angstroms and some change. Okay? So that means 912 angstroms, 910, 909, 852, 730, whatever. Those all can ionize hydrogen. So if there is a spectrum of light with all frequencies coming through, or wavelengths coming through into neutral hydrogen, the photons that have energies lower than 912 are mostly just going to pass right through. Anything that has a photon energy greater than 912 angstroms, or 13.6 eV, or a wavelength shorter than 912 angstroms, can be absorbed. And so you have this region where all the light can just get removed. Okay? This is called an ionization break. okay, or edge. And I'm going to show it to you in a minute. Okay, so this affects the overall continuum shape of the spectrum now, doesn't it? Okay, you wonder why in an A star it goes up, it goes up, it goes up. There's some absorption lines, and all of a sudden it tanks down like that. Why is there that drop? Because that's where hydrogen starts to get ionized. Those photons have enough energy to ionize hydrogen. Okay. All right, so this affects the continuum shape. Again, it really reflects the gas physics and the radiative transfer. Okay. This ionization break can be treated as an absorption line because it's an absorption process. Photon comes in, gets absorbed, its energy gets converted into the kinetic energy, well, potential energy to get it out of the potential well, plus the residual kinetic energy. Okay. So the difference is that this alpha cross-section is actually a smooth and continuous function and has a cutoff when the photon has a wavelength exactly equal to the ionization energy, the energy required to ionize, in this case for hydrogen, 13.6 electron volts. Okay, so let me show you some pictures. Okay, maybe I can zoom out one more. This is the cross-section in units of 10 to the minus 11 centimeters squared for the bound-bound absorption n equals 1 to n equals 2 in hydrogen, Lyman alpha. And I said there's a natural or physics atomic cross-section for it. This is the atomic cross-section right here, based upon a very hairy formula. It involves hypergeometric functions and overlap integrals of wave functions. It's real nasty stuff. But you can get out a closed form solution, it turns out, with hydrogen. Not so lucky with those other complicated atoms. Okay? And that function looks something like this. This function, actually, we'll talk about it later, the shape of this is called a Lorentzian, if you haven't heard of that before. Okay. Very peaked, and it shows you that the absorption due to that transition only absorbs a very narrow range of photon frequencies or wavelengths. Okay? This is 0.0002, I believe. And this is 6699. And this is a very, very range. The width of this line is about 10 to the minus 3 or 10 to the minus 4 angstroms. 1/10,000th of an angstrom. Very narrow region of wavelengths. Okay? The other broadening I was talking about is because the gas is hot, some of the atoms are moving toward the light, some are moving away. That's what broadens the line. But the actual individual atom only does a very, very narrow, I can't tell you how narrow this is. This is gossamer thin, delta function type stuff. You couldn't measure this with unless you had some kind of super Fourier, fast Fourier transform spectrograph. Okay? It's going to look like nothing. Okay. Anyway, this is the cross-section for absorption. Notice that it's very narrow. That's my point. Now, look at the wave scale here. This is the scale in wavelength from 912 angstroms all the way effectively down to the end of the electromagnetic spectrum. Through the UV, through the gamma rays, all the way to the high energies. Okay? The cross-section is 0 for photons with wavelengths longer than 912 angstroms, because those photons have energies lower than 13.6 eV. Once you get to right where you have photons at 912 and some change angstroms that have the energy to ionize the hydrogen, boom, the cross-section turns out to be around 6.3 times 10 to the minus 18 centimeters squared. Okay? Every astronomer should know that number. You may not know at the end of this semester, but when you grow up and become big PhD astronomers, everybody knows that the ionization edge of Lyman alpha is 13.6 times 10 to the minus 18 centimeters squared. It's just one of those numbers like your phone number that you end up learning. Okay. Now, that cross-section is a function of wavelength, and it turns out that, in a sense, the probability of absorption, or of ionization goes down as the energy of the photons go up. Very important to know. Very important to know. This is classic behavior of photons and ionization. Okay? The probability that a photon will ionize an atom is always the highest right at the ionization energy itself. In the case of hydrogen, that's 13.6 electron volts. Photons with 13.6 have the highest probability of ionizing a hydrogen. If you come through and you have a wavelength of 800 angstroms, you actually have higher energy, don't you? And so you think, oh, maybe my probability should be higher. I'm going to actually ionize that electron off of that hydrogen. But no, actually, the probability goes down.
Why is that?
That's a really, really good question. And I think it has to do with the amount of time that there's allowed for the impulse. You know, the frequency is faster, and so the response resonance of the electron to the transition, which is what really governs how you calculate the cross-section, that resonance is mismatched as much. So the resonance is higher here, and then the ability of the electron to respond within the time it takes the photon to go through is better matched at the ionization energy. As the photon frequency goes up, there's a mismatch between the impulse time and the frequency of the vibration for it to catch it. Okay, so as you go to higher and higher in energy, the cross-section, or the probability, I don't want to call cross-section probability, but it's easier to think of them that way, actually decreases. And it goes down basically almost as the cube of frequency. This curve is actually a lambda cubed, or a frequency to the -3, or a lambda to the 3rd power. You can see it there. Okay. It's not exactly that, but for your back of the hand or back of the envelope calculations, if you ever need to make one, you can just use that nice scaling law. Point, this is narrow, extremely narrow, and this is a huge swath of spectrum, so they can really affect the overall global shape of the spectrum. Any questions about that? So what happens is, let's consider neutral hydrogen. Okay. Here is a spectrum, wavelength, okay, relative intensity, I lambda over IC lambda, okay. Here is the Lyman alpha line, Lyman beta, Lyman gamma, Lyman delta, the series. Okay, this is that narrow profile that I was talking to you about. This broadening is due to the thermal properties of the gas. Otherwise, this thing would be thinner than a pixel on this diagram. Okay, but the fact that the gas has velocity spreads it out so that you see this absorption line. 1215.6017 is the center, broadened by, okay, is the optical depth greater than unity in the core? Yep, because this is where optical depth is unity, is right here and right here, because that's where 0.368 is. All right? Okay, there it is. Then you have, this is n equals 1 to n equals 2 absorption. Here's n equals 1 to 3. Here's n equals 1 to 4, n equals 1 to 5, etc., etc., etc. The optical depth is probably a little less than unity in the Lyman alpha. Okay, in other words, or Lyman gamma. Lyman gamma apparently the absorption from 1 to 4, 1 to 3, 1 to 4, is not as probable as, say, you could have the same flux of photons with 1215 angstroms as you do here at 975, and the hydrogen is more efficient at removing these photons than it is at removing those photons, because the cross-section is higher here than it is for there. Okay. That's why you get these lines weakening like this. Okay. Now, here's where 912 angstroms is. Okay, you can see all the flux has been removed. Okay. Remember what the cross-section looked like? Right? All of a sudden it appears out of nowhere at 912 angstroms and then goes as lambda cubed. Okay? So, This is very, very high optical depth everywhere here. Probably greater than 10 everywhere, because that flux is just wiped. The reason it's so strong is because the column density is so high. But as you reduce the column density, 10 to the 19, again, ionization edge is really solid. But once you get down to 10 to the 17.2, that's another magic number with hydrogen. 10 to the 17.2 atoms per centimeter squared. The optical depth becomes exactly unity at the edge. This is optical depth unity here, down to 0.368. I'm not sure that it worked. I think because I actually convolved these spectra with an instrumental spread function, so it modifies this a little bit. But this really, if I hadn't convolved it with an instrument spread function, it would go down to 0.368 and come back up. So here's your lambda to the third recovery, because the cross-section is decreasing as you go to higher energies and lower wavelengths. And here is the ionization edge here at optical depth unity. Okay, and then here is a column density of 10 to the 16.8. You can see that as column density goes down, the weaker lines from the down-bound transitions, but you see that the ionization edge again is weaker. Now, if I was to plot this all the way out, this spectrum, this would actually eventually recover back up to unity. This actually will come up as lambda cubed.
If you plotted it all the way out, it would like reflect the plot that you just showed of the probability.
Yes. So let's just draw that out. If I draw that out, it will go back up like that. In fact, I'll go ahead and draw that on the board for you. So what I've drawn is basically alpha, beta, gamma, whatever, blah, 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 and then I've got you out to about there. Okay? But really what would happen is you would watch this thing go back up like this. Right? Because the cross-section does this. I lambda over IC lambda. Okay, 1, 0. See what I'm saying? Because this cross-section is high here, the absorption is massive there. The cross-section gets weaker, and so the absorption goes down.
Because it becomes less probable for it to absorb.
Exactly. Okay. Exactly. Good stuff, people. Now, if you've ever heard of the Lyman edge in a quasar spectrum, that's where it comes from. Have you ever heard of a Balmer decrement in a star? Okay, I'll talk about that in just a minute. It's basically an ionization edge, but it's in the optical, not in, this is in the ultraviolet, because 1250, ultraviolet starts around 3,000 angstroms and below. 1250 is firmly in the ultraviolet. 912 is firmly in the ultraviolet. So all these Lyman series lines, n equals 1 to 2, n equals 1 to 3, n equals 1 to 4, are all in the ultraviolet. It's a series. Okay. Any questions? Okay. Is the camera still going, I hope?
Yeah.
Excellent. Okay. Right, so this is where I have what the different transitions are. In this case, I assumed a much hotter gas with 30 kilometers per second velocity distribution for my spectra. All right. So let's talk about some fundamental quantities, the equivalent width. I'm thinking everybody's heard of the equivalent width before. Talked about it a little bit last time we met. Okay. It is defined as an integral from beginning wavelength to an ending wavelength of 1 minus this equation of I lambda over IC lambda times d lambda. So this here is known, this quantity right here is known as the flux decrement. How much the flux has been reduced from unity. Okay? And basically what you're doing is you're finding the area under the absorption profile. So here's an example let me blow that up a little bit. Here's an example of a 10 to the 14.4 column density and a sigma of 15 kilometers per second gas. It's made an absorption profile here. Okay. Obviously, in the core, the optical depth is much greater than unity. The unity is about right there on the wing, right there. Right. Now, if you measure the area under this curve doing that integral, you'll get a number. That number can be geometrically pretended to be, I suppose, representative of a swath of spectrum completely removed that has a certain starting and ending wavelength. The difference between those two wavelengths will be, say, 0.2 angstroms or something like that. In this case, 0.21 angstroms. All of these have the same equivalent width, 0.21 angstroms. This difference here, you took that wavelength minus that wavelength, you're going to get 0.21 angstroms. So the area of that is equivalent to the integral under that curve. So that's why they call it the equivalent width. Okay. Here is another profile which has the same equivalent width. In other words, the same area removed under the integral. Now the log column density is 10 to the 13.71, and the velocity is very high at 45 kilometers per second sigma. And you get a much broader line, but you get a much shallower line. But the area, when you do this integral, has the same equivalent width. Same thing with this. So I had to hand draw it in a little bit. 10 to the 13.8, 30 kilometers per second gives you a deeper profile that's narrower, but the area under it is the same. Same with log 10 to the 13.67, b of 60, very broad, okay, and same equivalent width. Okay. I just happen to know how to make these calculations. Give me the equivalent width for this sigma, what's the column density, and you can make these profiles, okay?
Hey Chris?
Yes?
I think I may have been writing when you said this, but just to clarify, so
Yes.
the area of essentially that black box is the same as the area of the absorption feature?
Precisely.
Okay.
Precisely. And it's the width of the box in angstroms, you know, this minus this, which is the way we characterize it. The width of this box is 0.21 angstroms. Okay, so that we call that the equivalent width. Because though this is unitless, you have the dimensions of wavelength here in your integrand. So, because we've showed that optical depth is column density times cross-section, and you can write I lambda over IC lambda as x to the minus n alpha, excuse me, you can write the equivalent width in terms of n alpha or tau or whatever quantity that works for you. So this is another way of, if you know alpha, you can do this, solve this integral for the measured W. Because you can measure W directly from the spectrum itself. You don't have to do the integral. I can teach you later how you do that. So W, in a way, can be a sort of poor astronomer's way of getting the column density. And what do I mean by that? Well, if you have a low resolution spectrograph that doesn't resolve your lines very well, you can't really get information on the velocity spread of the gas. But if you assume something about the behavior of this, you can get the column density. And I'm not going to get into it now, but you can assume that this is equal to the instrumental spread function if you're what's called unresolved. But I'll get into that later. Okay. Anyway. Oh, by the way, you've heard me talk about sigma v, and now you've saw me talk about something called b. There's a relationship between the two that's involving the square root of 2. Again, we'll get into that later. This is really the sigma of the velocity along line of sight. This is a quantity we call the b parameter that spectroscopists use all the time. And I'll get into why that exists later, but I'm just introducing it now. All right, so that brings us to the curve of growth. Now, remember I told you that the curve of growth, and when we met last, was basically a relationship between column density and equivalent width. All right? I've had several people ask me for this plot. Apparently, there are people out there that believe it's a useful description of what's going on. Okay, instead of using column density, I'm going to use the optical depth at the core of the line. Okay, remember the plots I showed before, which showed the distribution of optical depth, and I said in the core of the line at the peak, that was the optical depth was like 1 or 2 or 4. That's what we're talking about at the line core, what the optical depth is. Okay, now this is a huge dynamic range in optical depth from 100th to 1/10 to 1. Now you know what that means now. You know what the flux ratio is going to be. It's going to be 0.368 for that. To 10 to 100, 1,000, 10,000, 100,000, a million, blah, 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 blah. Now, we're going to again do the Lyman alpha transition, the n equals 1 to n equals 2. Okay? So, for example, and then this is the equivalent width, which is that integral. So, let's look at these 3 points here. They're given by this point, that profile, this point, that profile, and this point, that profile. Okay? So, this has a optical depth of less than 1/10, maybe about 0.07 in the core. All right? And what did I use for the sigma on this? I forget what it is. It's probably 30 kilometers per second. Yeah, 30 kilometers per second. And then a velocity width of the gas of 30 kilometers per second. And that generates this little profile here. Now, if we increase the optical depth from 0.07 up to about 0.7, the depth of the line goes down, and notice that the width is not really much broader because it's the same velocity broadening. But we increase the optical depth, the line got deeper. We increase the optical depth even more, okay, the line got deeper. So what's happening is the equivalent width is going up in almost exact linear proportion to the central optical depth. In other words, as the central optical depth and the column density are effectively 1-to-1 correlated. So as the column density is going up, the equivalent width is going up. You go up an order of magnitude in optical depth or column density, you go up an order of magnitude in equivalent width. It's a 1-to-1 line on a log-log plot, and they call that the linear part of the curve of growth. Okay? And so that's what this thing over here at the side is saying. On the linear part, the equivalent width is directly proportional to the column density. Astronomers love the linear part of the curve of growth because you can measure the equivalent width and instantly get the column density independent of the B parameter. I'll talk about that in a minute. All right, let's consider now going over this change of regime to what we call the flat part or logarithmic part of the curve of growth. This happens for Lyman alpha because these transitions happen at different column densities for different elements and even different transitions. This is Lyman alpha of hydrogen. If I did Lyman beta of hydrogen, the equivalent width line will be down lower, and these transition areas will be at different central lines. So each transition has its own precise curve of growth. Okay. All right. Now, in this regime, let's look at optical depth of about 20, and we get an equivalent width of about 0.7. Okay, and that's this profile right here. Notice that with optical depth of 20 in the core, obviously nothing's really getting through. We're saturated completely in the line core. Now, I'm going to increase the optical depth to almost 1,000. That's this line here. Okay. What's happened now is that the profile, the equivalent width has gone up. So you can see the area is bigger, but it hasn't really gone up that much. Even though we went up an order of magnitude or more here in the column density, the equivalent width did not increase that much. And it only increased because the wings got, more flux got taken out in the extremes. Do you remember what causes the light to get removed in the extremes?
The velocity dispersion.
The velocity dispersion. Okay. So what's happened is we've added more atoms to the gas. We've added more atoms that are moving at slow velocities to us. We've added more atoms that are moving at faster velocities to us. So since there's more atoms at faster velocity, the total effect of absorption at higher velocity have gone up. And then we've added more atoms at the lower velocities that are moving away from us. So basically what you've done by adding more atoms is you've added more atoms that are going at the more extreme velocity. You've added more atoms at all velocities, but that's increased the number of atoms at those extreme velocities such that the optical depth now has gone up in those regions. This is probably one of the key things to understand about absorption lines and gas physics, and we'll talk about it multiple times throughout the course. If I didn't say it in a way that completely makes sense to you right now, hopefully we'll say it a lot of different ways and it will come up. But that's what's giving rise to the broader line, and because it's only the high velocity distributions of atoms toward you and away from you that are contributing the extra flux removal, the equivalent width does not increase very much. Called the logarithmic or flat part of the curve of growth. If you must know, the equivalent width then will scale directly with the B parameter and the square root of the log of the column density divided by the B parameter. I can show this derivation to you later in the course, but this is the basic thing. Now, so in other words, we're going to find something here that, notice that the equivalent width is very proportional to the velocity distribution of the gas. So really, what we're going to find here is that this part is really mostly sensitive to the velocity. I'm going to talk about that in a minute. The linear part, there's no appearance of the sigma of the gas or the B parameter. So if you know N, you know equivalent width. If you know equivalent width, you know N. Ah, that's great. You measure the equivalent width, you've got N in this part. You measure the equivalent width here, you can't get N unless you know what the velocity dispersion is, unfortunately. Okay. All right.
So as the equivalent width changes as you add or you increase the column density, but it changes for different reasons in the different regions. Like it changes more because of velocity dispersion in one part, and then more because of pressure broadening or something in other parts.
Right. So what's happened is, let me draw this. And more and more, I think I should say things and actually draw what I mean about it. So this is on camera here, right? Is the green pen actually coming up by any chance?
You just erased the green pen.
I'm going to go with the black now, so it might be better. Okay. So this is the distribution of velocities of your atoms in a V. This is a distribution, okay? So you have a distribution of atoms, some at high velocity, some at, call that 0. So these are atoms that are rest with respect to you along the line of sight. These are atoms that are moving away from you, and these are atoms that are moving toward you, okay? So minus and plus. Okay. Notice that there are very few atoms moving away from you at high velocities or toward you, all right? So what's going to happen then is your optical depth is going to end up looking something like, there's one. We'll do something like that. Basically following this, because there's more atoms at that velocity, there are more optical depth because there's more absorbers. And there's very few moving toward you at high velocity, so the optical depth is small, etc. Now, watch what happens. And I'm hoping the green comes through on the video. Let's increase the column density. That's the same as increasing this distribution upwards. Notice now at, say, this velocity, we have a lot more atoms now contributing at that velocity than there used to be. And so now your absorption, your optical depth, is going to do something like this. And And now you have unity optical depth out, all the way out here, whereas before you didn't have unity optical depth except in this region, greater than unity. Now you've got greater than unity optical depth over this whole region. And so your profiles for the small column density, smaller optical depth distribution is going to look something like this. Okay. But this profile, you're going to get, you have more atoms at these extreme velocities, so you have unity optical depth out here. It's going to come down to about there. You're going to get something that looks like this. That's a shitty line, but you get the point. Right. Now, that's not exactly this particular illustration. I kind of drew a line here and a line there. You know, I drew like this line and that line in my example. But do you see how you get the point? You get the point? Is this basically what you're doing? You're saying pour more atoms into the gas. Now you have more atoms at every velocity. Because you have more atoms at every velocity, your optical depth has gone up at every velocity, or absorption wavelength. So now, even at these areas where you wouldn't have seen absorption because you just didn't have enough atoms to give you a high optical depth, more atoms, you have more atoms to give you, you can get more optical depth at these extreme velocities, and so you get a broader absorption line. Okay. Hope that answered that. Okay. And we are effectively at the end of our line. So let me just finish with the last part of the curve of growth. This is called the square root part, and I want you to notice a regime change. And I can't get into it now because we're ending class, but this is where you change away from this whole story that I just told you and drew like a kindergartner. I apologize. We're going to get into another story that's called damping, and getting into something called damping wings. I can't get into it today because class ends. But I want you to look at this graph and notice something very different. Look at the range here. This is 1215.6701. This is an angstrom. Same here. This is an angstrom. These equivalent widths are on the order of a tenth to an angstrom of width. Okay? Look at this one. This is now 20 angstroms wide from here to here. Okay. We have taken this and stretched it out, so it's the whole size of the board. Okay, so you can imagine that this profile would literally, on this scale, drawn on this board, would do this across this whole board. It is a huge swath of spectrum, relatively speaking. Something else happens in here. We get into what's called dampening. This has to do with actually, it's an atomic physics thing that has to do with the broadening of the energy levels. It can be related to the Heisenberg uncertainty principle, delta E times delta T equals H bar, but that's kind of the semi-classical childhood way to look at it. But that does give you a good illustration. The point is the energy levels get blurred of the upper bound and the lower bound transition energies of the electron. And so you get this tremendous broadening effect that are the Lorentzian wings. So this is right here at 10 to the 4 optical depth is that very narrow absorption line. Okay. Well, at least we only got interrupted twice.
Yeah.
And this absorption line here with about 10 to the 5 optical depth, okay, is given by that. Notice what's happening here now is that you're not really broadening the Doppler wings in the core, which is now the core. You're actually starting to get these damping wings. Okay, and then you come up here to 10 to the 6, 1,000,000 optical depth in the line core. Basically now you have this tremendous blurring of the energy levels, and you get this very broad profile that, if taken on this scale and put on the board, that profile, like I said, would go all the way across this board. Those are huge, and it causes the equivalent width to rise rapidly. Now, in this regime, again, you only depend on column density, but you'll notice that the slope of this is linear into the 1. The slope of this is to the half power. Okay, so this damped part is sometimes called the square root part of the curve of growth. Linear, kind of flattish, square root. Okay, slope is a half, slope is 1. Okay, that is the anatomy of the curve of growth, and I'm hoping that you understand why the equivalent width only changes very little on the flat part, even though they were kind of kindergarten pictures. We'll get into this later, why these behave this way. And when we come back, we'll finish up how the B parameter affects the linear part of the curve of growth, and we'll talk about the conditions of the solar atmosphere and talk about why the spectra have these shapes. For example, I'm just going to say it real quick. What's that look like to you? Huh? That looks like an ionization edge to me. Okay, so we'll get into that a little bit, and then we'll finish with this hand-drawn picture of mine showing the infrared, optical, and UV part of this. Okay, thanks for listening, and I'm going to look at your quizzes and hand them back to you. It gives me an idea of what stuck, and if you don't mind, I'm probably going to throw another brief one at you. And these are not graded; these are just feedback. And hope if you don't like them, come see me in private, and maybe I'll modify what I'm doing. But I think it's a good thing. And if you like it, you could also tell me you like it. Feedback's good, no matter what kind it is. Okay. All right, thanks. We'll see you guys next time.